All right, here we go. Coterminal angles, arc length, and linear and angular speed. Please make sure that you know your Greek letters, theta, beta, gamma, and alpha. Okay? Know what to call them. So today we're going to talk about coterminal angles. Coterminal angles are just two angles with the same initial side and terminal side, the same start and the same stop. So if you look at what you did for homework last night, when you did problem number 56, if you look at problem number 56 from your homework, problem number 56 said 405 degrees. Well, to graph that, what you did was you knew it was one full rotation plus an extra 45 degrees. So you've basically just graphed 45 degrees. So 45 degrees is going to be coterminal to 405. Same thing here. Here you see 420 goes all the way around and then a little and winds up right there. 60 again goes all the way around a little, except it doesn't go all the way around. This time it just starts here and goes up and winds up at the same spot. So that means 420 and 60 are coterminal. So we used coterminal angles yesterday when we were graphing these angles greater than 360. We just didn't call them coterminal. With the negatives, how do we have negative angles? Negative angles come from clockwise rotations. So here we have this clockwise of 120 degrees as we come from here to here. So what would happen if I went the appropriate direction, the counterclockwise? Where would I end up? I would end up right here at 240 degrees. Okay? Questions? Okay. All right, so let's look at some examples. When we're talking about angles such as 390, there's two different ways that we could go about finding this. So the first one kind of goes with what we did yesterday. So if we were to graph 390 degrees, we would take and graph it as a full 360 degree rotation plus an extra 30 degrees. So here your answer, your coterminal angle, is that extra 30 degrees. Questions? All right, the other way we can go about doing it, and really it's the exact same thing, we're just writing it a little differently. What we're going to do is we're going to subtract 360 until we get a value that is a positive value less than 360 degrees. So 405 minus 360 is 45. So my coterminal angle to 405 is a 45 degree angle. Questions? Go ahead.
Can there be two coterminals to the first one?
There can be an infinite number of coterminals.
So I was thinking like negative 330 would be the same thing as 30 degrees.
Mm-hmm. So negative 330 would be the same thing. 750 would also graph in the same place. So here we're specifically asked to find one that is a positive angle less than 360. But yeah, there's an infinite number of coterminal angles. All right, negative 135 degrees. So if you think about where we would put negative 135 degrees, that's going to be a clockwise rotation from your positive x-axis. So as we go in a clockwise manner from our positive x-axis, 135 degrees, what we really need to find is what's the other half. So how would I find the other half of that? I'm going to find the difference between 360 and 135. And we get 225. So here our coterminal angle is 225 degrees. Questions? All right. 11 pi over 4. So now here we need to think about our radians. So now we need something that is less than 2 pi. Why less than 2 pi? Because it's 360 degrees. Good. Okay. So how would I express 2 pi as fourths? 8 pi over 4. So what we're going to do is we're going to use the same process, but we're going to talk about it in terms of radians. So what we're going to do is we're going to subtract 8 pi over 4, and we're going to keep doing that until we get a number that's less than our 2 pi. So 11 pi over 4 minus 8 pi over 4 happens to give us 3 pi over 4, and is 3 pi over 4 less than 2 pi? All right, so that makes that your coterminal angle. Questions? Go ahead. No. If you're given radians, we're going to stay in radians. If you're given degrees, you're going to stay in degrees. Okay? In fact, if every time you have a problem where we're talking radians and degrees and you're constantly changing your units back and forth, that's going to leave you open for more mistakes. The more math you do, the more math mistakes you leave yourself open for. So the goal here is to get yourself completely, totally comfortable with radians. All right. Negative 5 pi over 6. So now I have a negative angle. So in number 3, we added 360. So what is the radian equivalent? 2 pi. But how do I express 2 pi with a denominator of 6? 12 pi, good. And we get? 7 pi over 6. Good. Nice and loud. Be proud of your answer. 17 pi over 6. So now here, again, we're going to subtract 12 pi over 6 until we get a value that is less than 2 pi, but still positive. And here we get 5 pi over 6. So our coterminal angle is 5 pi over 6. Are there any questions? All right, I want you guys to try 855 degrees on your own. All right, who is my answer for me? Jesse, what'd you get?
There's 7, I got 135 degrees.
Why 135 degrees?
Because there's 2 rotations.
Mm-hmm. Perfect. All right, 25 pi over 6. How many extra rotations do I have in positive 25 pi over 6? Good. So I have 2 full rotations. How to express 2 full rotations in terms of sixths of pi's? But 12 pi over 6 is 1, so 2 would be 24 pi over 6. So when the book uses the notation of k times 360, all they're saying is how many full rotations are there in the degrees that you're given or in the radians that you're given. Okay? So now here with number 9, we have to go the opposite way. So now we have negative 25 pi over 6. So if we were to add 24 pi over 6, I would get negative 1 pi over 6. Well, I'm not there yet then. So I have to add one more 12 pi over 6 to get our answer of 11 pi over 6. Good. Questions? Go ahead.
But can't negative 1 pi over 6 just go the other way?
Right, but remember, we want
It has to be positive?
a positive angle less than 360 or 2 pi.
You put 330 degrees instead.
For number 9? No, if you're given radians, you keep radians.
Like I just went from negative 1/6 to 330. Or just, you have to stay there.
If you're given radians, you have to stay in radians, yes. Other questions? All right. So on Tuesday, when we first started talking about radians, we defined radians as using the formula arc length divided by radius is the number of radians in the angle. So what we're going to do is we're now going to rearrange that formula to use the number of radians in the circle and the length of the radius to find our arc length. Okay? And to do that, now here with radians, it's super duper easy. It's a little bit more difficult with degrees. With radians, all you have to do is multiply the number of radians times your radius, and you're left with your arc length. Make sense? Okay, just make sure that you get the formula written down. You don't need the full paragraph written down. Okay? All right, so let's look at a few examples. So I have a circle with a radius of 10 inches. Find the length of the intercepted arc by a central angle of 120 degrees. So this is the first time and the last time you're going to get the hint. The hint is to start by converting to radians. Because to work with our radiuses, we need our radians. So we identify radius. Radius is 10 inches. And we identify theta. Theta is 120 degrees. But what is my radian equivalent to 120 degrees? 2 pi over 3. All right, so what's my arc length? Well, my arc length is radius times radians, which gives me 20 pi inches over 3. Now, 20 pi inches isn't really a useful measurement. When was the last time you went to the doctor and the doctor said to you, you are 4 pi feet tall? Okay, so keeping a measurement in terms of pi isn't really useful when we're talking about things like inches, meters, feet, that sort of stuff. So on these, you're going to give me 2 answers on the test. On the test and on the quiz, I want to see 2 answers. I want to see the answer here as shown in terms of pi, and then I want you to calculate the answer to 2 decimal places. So I put this in my calculator, 20 times pi divided by 3. 20.94 inches. So that's a slightly more useful measurement. Questions on that one? All right. Now let's talk about a circle with a radius of 6 inches. Now we're going to find the length of the arc intercepted by a central angle of 45 degrees. So again, I have this radius of 6 inches. and an angle of 45 degrees, but again, degrees is not helpful in this situation. I need radians. Pi over 4 radians, good. You guys are going to get to the point where these key ones that we use a lot, you're just going to know them off the top of your head, okay? So what is my arc length? 6 over 1 times pi over 4. Make sure you include your unit of measure. So we have 3 pi over 2 inches. But again, 3 pi over 2 inches isn't the most useful measurement on the face of the earth.
Is that in terms of pi right there? That answer?
Well, is there a pi in the answer?
Yeah.
Then it's in terms of pi. Okay, so now let's take it out of terms of pi and bring it to 2 decimal places. 4.7. Okay, I want to take a time out and talk about units of measure. Okay, especially moving forward to the next topic. One of the things, and I'm guilty of it myself, is a lot of your previous teachers have kind of let the unit go by the wayside. So they haven't made you write down your units in your problem and in your answer. So here, as we're moving forward, it's really important that we get back in the habit of writing down our units whenever we have a unit. Okay, so here we want to keep the inches. Especially once we start converting units. When we convert units, we want to write down our units so we make sure we're canceling the correct thing. Okay? Questions? All right. Pencils down, don't write this down. These tables are in your textbook. I believe it's right about page 493. Okay, so the first one here is on page 493. And then the second one here is on page 494. So make a note to yourself to go ahead and copy this down out of the book when you get a chance. But this looks really confusing and really complicated, right? It's not. Okay, you don't need all this gibberish. What is angular speed? Let's talk about angular speed first. Angular speed tells you how long did it take to get around the circle. So if you're on a Ferris wheel and you're riding in your little bucket and your Ferris wheel is going so fast, how long did it take you to complete one full rotation on the Ferris wheel? That's all angular speed says. Linear speed basically boils down to, if I could take your distance, so we can agree that even though we end at the same point, when we go around a circle in the Ferris wheel, we've traveled a distance. So if I can take that distance kind of like a string and straighten it out, now how fast did you go that straight string distance? That's all linear speed says, is, okay, we moved. How far did we move and how fast did it take us to get there? Okay? So angular speed is the number of revolutions per unit. So here we're told that a tire has 4 rotations per minute. Well, rotations isn't a very good unit of measure. Rotations is not a universal measurement, because your rotation, quote unquote, is going to change depending on the size of the circle. So let's get it to something that's more of a universal unit of measure. Radians per minute. Okay, so now the variable that represents angular speed is the variable W. W represents angular speed. So right now our current measurement of angular speed is 4 rotations per minute. Well, I don't want rotations per minute, I want radians per minute. So I'm going to cancel my rotations. So that means rotations goes in the bottom. And I want to replace rotations with radians. In one rotation, how many radians is that? One go around a circle. 2 pi. So that means that there are 2 pi radians per rotation. The book tries to make it sound really complicated. It's not. This is always your first step. Whenever you're asked about speed, linear speed, angular speed, your first step is always to just multiply by 2 pi radians over 1 rotation, so we can get it in radians per minute, radians per second, whatever it is we're measuring. So here we end up with our rotations canceling, and we're left with 8 pi radians per minute. Now, doesn't 8 pi radians mean the same thing as 4 go-rounds on a circle? Yeah. Okay. So we're just putting it in a more manageable unit of measurement. Questions? All right, so whether you're on you're a little fly on a little circle that has a radius of 2 inches, or you're a big squished fly on the tire of a Big Mac truck, okay? That didn't make sense. You know, if that wheel that you're on goes around 4 times in a minute, doesn't matter how big of a circle you're on, you're going 8 pi radians per minute. Now, the linear speed says if you're on a little circle, well, think about the circumference of a little circle. And if I were to flatten that circumference out, that's going to be a shorter distance than, say, that huge truck tire if I were to take the circumference and flatten that out into a distance. So that's what linear speed says. Linear speed says, okay, I went around the circle 4 times. How far did I travel as I was going around the circle 4 times? And that's your linear speed. Linear speed uses a variable v. And to find linear speed, all you do is take your radius and multiply it by your angular speed. Okay, because remember, the radius of the circle is what tells you the circumference. Okay? So I have a tire with a radius of 8 inches. So I'm going to travel 8 inches times 8 pi radians. Now here we start leaving off the radian. The book stops writing the radian. Now if there's a little tiny circle that means degree, it's in degrees. If that little tiny circle isn't there, it's in radians. And you're especially assured that it's a radian measurement if there's a pi involved. Okay? So 8 pi per minute. So we set it over to 1, and we multiply just like we would any other time. And we get 64 pi inches per minute. So in 1 minute, if you're sitting on this tire, in 1 minute, you will travel 64 pi inches. Well, again, telling you that you're 4 pi feet tall doesn't really help. That's not a useful measurement, okay? So one more time, we're going to answer with 2 answers. Our first answer is going to be this one that we've just found in terms of pi. Our second answer is going to be converted to 2 decimal places so that we have a more relatable measurement. So we take 64, multiply by pi, and we get 201.06. Inches per minute. Questions? So this is a 2-step process, and the 2 steps are always the same. Your first step is always to multiply by 2 pi radians over 1 rotation to get it in terms of radians. And then your second step is always to multiply by the radius. Those are the only two things you have to do to find angular and linear speed. So let's look at another example. All right, a hard drive in a computer rotates at 3,600 revolutions per minute. So our current angular speed measurement is 3,600 revolutions per minute. All right, well, I don't want revolutions per minute. I want radians per minute. So again, the first step, always the same. This is equal to 2 pi radians per 1 revolution. So technically we've multiplied by 1, so we haven't really changed the value. But again, one more time, our revolutions cancel, and we're left with 7,200 pi radians per minute. Questions so far? All right, and then now we're going to use the angular speed, that W, to find your linear speeds. Remember, linear speed is just our previous answer multiplied by radius. So here our radius is 2 inches. We're going to multiply that by our angular speed, 7,200 pi per minute. And we get 14,400 pi inches, bless you, per minute. So that's our first answer. What's our second answer? Times it by pi. And we get 45,238.93 inches per minute. So if you were to put a little spool of thread on that hard drive, think about how fast those hard drives spin. So if we were to put that string on there and let it unwind itself as it went around the circle, after 1 minute, we'd have 45,238.93 inches of string. After 1 minute. Questions? Go ahead.
If it's the same distance, then how is it a different final product?
What do you mean if it's the same distance? It's not, because the radiuses are different. So if you have a radius of 2 inches and you have 4 rotations a minute, and if you have a radius of 10 inches and you have 4 rotations per minute, you're going to have a total travel length that's more the bigger the radius is.
Right, but if you take that bigger radius, let's say the radius is 2 here,
Right?
I don't know if there's a question.
Like, why is this answer so much bigger than our last answer?
Yeah.
Well, because we're going around faster. And our last answer, in our last question, we only went around the circle 4 times per minute. Now we're going around the circle 3,600 times per minute. So we're moving at a faster rate of speed. So think about driving in a car. If you have 2 cars right next to each other, one drives slow, one drives fast, the faster car is gonna get further at the end of a minute. Okay? All right, I want you guys to try this next one on your own. When do we do that? So now we're going to talk about a wind machine. It's going to generate electricity. The blades are 10 feet in length, and the propeller rotates 4 revolutions per second. So that means one blade goes around the circle 4 times every second. No, we're going to leave it in seconds. Okay, we want our final answer in feet per second. Alright, so your first step should have been to take your original angular speed of 4 revolutions per second and translate that into radians per second. So that's 2 pi radians per revolution. Again, our unit of revolution cancels. And we're left with 8 pi radians per second. So now, how far did I go? Well, if my radius is 10 feet, and I'm traveling at 8 pi radians, but again, we don't include that measurement, per second, then I travel 80 pi feet per second. And again, we want to include our answer in a more useful form, and 80 times pi is 251.33. Feet per second. Questions? All right, there's your homework. Get it copied down.